Hi. Welcome to my video. Today let's talk about the band structure, the music of electrons. Have you ever wondered why some materials are conductive, while others are not? The answer lies in the band structure of the material. In essence, the band structure is like a musical score that describes how electrons move through a material, just like how different musical notes create different melodies. Different band structures create different electrical properties. Now, let's imagine that we're in a concert hall and the band is about to start playing. The conductor raises his baton and the music begins.
We're having trouble. They kept telling me that I was turning my microphone off while I wasn't.
The sound waves travel through the air and reach our ears, creating a beautiful melody. Similarly, in a material with a good band structure, electrons can move freely through the material, creating an electrical current. But what happens when the band structure is disrupted? Just like how a missed note can ruin a melody, a disrupted band structure can cause electrical resistance. This is why some materials are conductive while others are not. Let's learn about conductivity and semiconductors. Much of our technology relies on substances that can conduct electricity, meaning that they allow the flow of an electrical current. But what is it about a material that allows it to do this? If insulators are things that do not conduct electricity, why is that the case? What are semiconductors, and where do they fit in? Let's learn all of these. So as we said, conductors conduct electricity, and insulators do not. While semiconductors are materials that have a conductivity in between that of a conductor and an insulator. Because of this intermediate conductivity, semiconductors can be controlled and used for technological purposes. The explanation for the conductivity of these substances requires that we take a look at molecular orbitals in metals and network solids. In order to put things into perspective, we must understand that these materials are not small molecules comprised of a handful of atoms, but rather, these are a huge arrays of a particular atom, or repeating formula unit, stretching endlessly in every direction. We know that when two atomic orbitals combine, two molecular orbitals will be generated, one lower energy bonding orbital, and one higher energy anti-bonding orbital. Thus, as more and more covalent bonds form, more molecular orbitals will be generated to house all of these electrons. Let's take a look.
An s orbital has a spherical shape. S orbitals on different atoms can combine to form molecular orbitals. As two hydrogen 1s orbitals approach one another, the orbitals combine with an increased electron density between the atoms. The result is a sigma bonding orbital. S orbitals on different atoms can also combine by subtracting the two 1s orbitals. A decrease in the electron density between the atoms is observed, resulting in the formation of a sigma anti-bonding molecular orbital.
Band theory. Here we can see the molecular orbitals involved as many atoms come together to make a network solid that will be a conductor. As the number of atoms increases from 1 to 2 to 4, to a number so large that it can be compared with infinity for practical purposes, the number of orbitals will increase in the same way, and as the number of orbitals becomes incredibly large, they will begin to resemble one continuous band. It is noteworthy to mention a few significant aspects of this concept, which we refer to as band theory. Since the lower energy bonding orbitals fill up first, while the higher energy anti-bonding orbitals are left empty, the atoms are first bound together by electrons in these orbitals. Second, the essential characteristic of a conductor is that electrons can flow easily between orbitals. since the energy difference between the highest occupied molecular orbital and the lowest vacant molecular orbital in a conductor is minuscule, that permits it to carry electrical current. When contrasting substances with different conductivities, we will observe something known as a band gap. This is an energy gap between the antibonding orbitals, also known as the conduction band, and the bonding orbitals, also known as the valence band. The substance is named this way because electrons need to reach these orbitals in order for it to conduct electricity. As previously stated, conductors have either no band gap or a very small one, allowing electrons to move freely. Because of their wide band gaps, insulators prevent the formation of currents. Conversely, semiconductors have a sufficiently tiny band gap that allows thermal energy to move some electrons into the conduction band's antibonding orbitals and maintain part of the valence band's bonding orbitals unoccupied. Because more thermal energy is available to push electrons into the conduction band and so allow for the formation of a larger current. This explains why semiconductors conduct electricity more effectively at higher temperatures. So what kinds of materials can act as semiconductors? These popular compounds are listed with their corresponding band gaps in electron volts so that we can obtain an idea of the acceptable range. We'll see that some of these materials are compounds, like lead sulfide, and some are elements, like germanium and silicon.